Hello again and welcome. Today I'm going to continue my series on waveguides. This will be part 3. If you look around you can see I have several horn antennas on the bench. After posting the last video, somebody had mentioned that Signal Path's channel had made a video on 3D printed waveguides. So during this video I'd like to go over some of my own testing of 3D printed parts. So we'll be looking at the radiation pattern as well as the VSWR for these different horns. Of course, when we're looking at the radiation patterns, that's a relative measurement. So it doesn't require any kind of calibration, but to measure VSWR, where it's an absolute number, now we have to calibrate the instrument, and of course that raises some questions even how to make that measurement. So I'd like to go over that as well. And the last thing I'd like to go over is possibly using the waveguide to identify different materials. So if you've watched the first two videos, you know that this is my frequency extender for the LiteVNA. Again, this is taking the frequencies below 4 gigahertz on the LiteVNA and then converting that from 8 to 12 gigahertz or the X band. This allows us to increase the dynamic range of the LiteVNA. And again, the way that this basically works is we're taking the output on port 1 of the VNA, we're running through a low pass filter, and we're mixing that with a frequency that's much higher than what the LiteVNA runs at. So this is our local oscillator here. This one happens to be running at 7.86 gigahertz. This runs through a splitter, runs through a mixer. We have an image rejection filter, and then an amplifier over here, and then an attenuator to help with the matching. And then this circles back through, goes through another attenuator up here to another mixer, which is also connected to our local oscillator. This is doing our down conversion. This one's performing our up conversion. And then we have another amplifier to the left to take up the losses of this mixer, and again through another low pass filter. This is a typical high power directional coupler. We can see this one is made by Narda. It's a part number 3044B-10, so it's a 10 dB coupler. You can see this is rated for 3.7 to 8.3 gigahertz. You can see it's fairly flat, or well within a half a dB. Now this coupler could be added to our frequency extender, basically taking the output of port 1 here and then driving that into the input here. So out here would be our load, and here's our reflected signal. This reflected signal is going to go to port 2 of the extender. Now again, the reason that I bring this coupler up is I talked about measuring these horns VSWR, and the way that we do that is we have to look at S11, not S21 like we've been using this extender for. One of the things that I forgot to mention about using a coupler with this extender or using a coupler with the VNA directly, of course the obvious problem with doing that is we're no longer using the directional coupler that's built into the VNA. We're using this, which means that port 2 becomes the reflected signal. What that means as far as my software is concerned, I have to make port 2 the data for port 1. So just keep that in mind. I had mentioned that in a video a long time ago. Somebody was talking about trying to measure antennas. It was a ham operator, and I guess they had some radio station that was local that was screwing up their measurements. And I talked about putting an amplifier on the output of the VNA to basically increase the signal to noise ratio. So you would drive that into an external coupler and then feed that back. And I set up a little experiment with that. I didn't go so far as to make the measurement because the software at that time didn't have the ability to flip the port, but I've gone ahead and added that feature for these experiments. Again, this is our homemade slotted waveguide, and I showed how I could use this to measure frequency, but again, I also talked about how this can be used to measure VSWR. Unfortunately, our homemade waveguide dimensionally isn't accurate. The other problem, you'll notice we don't have a flange. So to measure VSWR, we'd somehow have to couple this horn up to this waveguide. Now in the background, you can see there's this other device here. These are actually components that were part of a kit that was used at various universities to teach microwave theory. On the far left, this is a solid state oscillator. Here's a variable attenuator. You may recognize this by the slot. So this is our slotted waveguide, and this is our detector probe, and off to the far right this is our transition. Now I don't have the entire kit, so they had a control box that ran these experiments that had all the meters and speakers and whatnot in it. When it was first introduced, it was meant to drive a vacuum tube oscillator, but later on the kits included these solid state ones. In the manual they talk about basically using the filament voltage for the tube. Now what I found is these oscillators run on DC. They don't require a lot of current, so basically you go between pin 2 and 7, and again the polarity doesn't matter. And this particular oscillator puts out 10.5 gigahertz. So these training kits from the university actually are a WR90 waveguide. So you can see this horn mounts right up to this transition. No problems at all. So instead of trying to cobble something together with our homemade slide, what we can do is we can attach our antenna directly to this slide. Then we can use this setup to measure the VSWR. You'll notice that the two flanges were actually held together with some paper clips. For my own testing, that seems to be adequate. I've seen tools that you can slide down inside the waveguide to basically align them. I think for these experiments I'm going to show you, it's not going to be that critical. I'd like to talk a little bit about how we're going to measure these antennas. So my setup will have two horns. One of them will be a reference horn, and then the second one will be the horn that we're trying to test. One horn will be connected to the VNA's port 1, the other one to port 2. So in this particular configuration, we're using the DUT as the transmit side, and our reference is the receive side. Now for a DUT, we'd like to be able to rotate this not only around this way, but we'd like to be able to rotate it this way as well. So this is our elevation, this will be our azimuth. You can imagine with the horns, assuming that we have the polarization set correctly, is I'm rotating this horn in this axis, or this axis, we're going to end up with a radiation pattern that looks something like this. So of course you can imagine if we want any kind of resolution, to do this type of testing manually is out of the question. So how do we automate that? And I've shown this setup before. Here we have a couple of M-drive stepper motors which are attached to these gear drives. This allows me to tilt the antenna as well as rotate it. This bracket is made to hold the waveguide. So you can see it just fits around like so. And we run our bolts through and that holds it quite rigid. And then we have a piece of high flexible coax here which wraps around our mast. This rotor is then attached to our tripod, and then our reference antenna is placed at a stationary point, and then we just align everything up and we can take our measurements with this. So for our reference antenna, obviously we need something that works at the same frequency as our DUTs. So what we're going to be doing is using another horn. So actually I have two of these horns. One of these becomes the reference. Now again, these horns are a waveguide and we need to get down to coax. What we'll be doing is using our university couplers. So I have more than one of these. There'll be one located on our reference antenna, and then we'll be using the other one for the antennas that we plan to test. These parts that came with this university kit are not the greatest quality. The students aren't trying to make metrology grade measurements, but in this particular case it doesn't really hurt, because what we're trying to do is compare a bunch of antennas with each other. So any errors that are caused by these transitions or the distance really doesn't come into play. As long as we don't change anything in the environment, we should be able to get a decent measurement. Now I had mentioned the distance between the two horns. Of course, we have to be out in the far field, and there are equations to calculate what that is. Now from the papers I've read, you actually have to multiply that far field by another factor. Unfortunately, I'm kind of limited in my lab here how far I can get these two apart. We'll easily be in the far field, and we'll be holding this distance constant throughout our test. So again, we're just trying to eliminate variables. So in part 1, I had showed a couple of homemade horns. These were made out of circuit board material, and I've included the transition. So you'll notice that this horn is very close dimensionally to this horn, and there's a reason for that. I was trying to see how this circuit board horn compared against this purchased horn. In signal pass video, I think he was trying to make an absolute measurement. I don't think he was like comparing two horns against each other, and I think he was just trying to evaluate the forward gain of the horn. What I'd like to do in this test is compare different horns with one another and just try to get an idea which ones work the best. So in signal pass video, he used this MG Chemicals. This is a silver coated copper conductive paint. So what I'd like to do is repeat his test as far as using this material, but I want to try some other things as well. So again, this is one of our test horns. You can see this one is just the raw material. It's not been prepped at all. And by prep, I mean it hasn't been sanded or primed or anything. This is right off of the printer. So what we've done is we've printed several horns using different materials, and then I've prepped the surfaces differently on those as well. You can see how the surface finish on this one is quite smooth. So what I've done is I've wet sanded off all of the ridges, and then I've primed this surface, and then I've gone ahead and painted it. The other thing is I tried to play around with different coating thicknesses. I started off with just 2 coats, and then I measured the resistance, and I did that diagonally. So you'll see on this horn there's 2 dots. There's one up in the corner here and one here. So I'm doing a 4-wire Kelvin measurement, and I'm clipping around the flange and up at the other end of the horn, and then I'm measuring the resistance across it. This particular horn, for example, is 0.370 ohms when measuring it that way. Now some horns were made out of a conductive plastic. This plastic is made for ESD use. This particular one, making that measurement, is 680 k ohms. This is a conductive plastic. One of the things I was curious is if we could plate this plastic. So I took a piece of filament and I made up some solution, and I was actually able to plate that, but unfortunately it took about a half an hour to get enough plating on that plastic. So I tried this with some homemade transitions. Again, this is a 3D printed transition here, and you'll see what's happened. Of course, the plastic gets soft and it collapses. So I tried plating another piece. This is over, again, about a half an hour. I did it at a very low current. You can see the copper is starting to take, but I don't think that this is going to work out. This is definitely a better way to go. Now I've tried to apply this coating and then plate copper over the top of this, and what ended up happening is my solution basically ate this coating. So that turned out to be a total bust. There are a lot of videos on YouTube that talk about plating 3D printed plastic parts. That's a tongue twister. Unfortunately, a lot of those videos are for cosmetic purposes. We're trying to do it for an electrical purpose. I think to better evaluate that, I would go to a professional plating house to have that done. You'll notice that I have 2 different size antennas that we're looking at. There's these smaller ones as well as the larger ones. So I started out testing these smaller ones, and the reason that I did that is, of course, it's less material, so it's faster at printing, and it's less time as far as sanding and painting. And then as I kind of got a handle on how these performed, then we went ahead and started processing the larger horns. The only thing I'd like to point out is that I've read various papers where they've printed 3D horns like this and tried to show their performance, and there's a couple of problems that I see with a lot of the papers, and I believe that this would be a problem with signal path testing as well, is that they are typically running at much higher frequencies. Again, there's a reason that I chose to work with the WR90 waveguide. Yes, it's a lower frequency, but mechanically it's a lot more forgiving. So as you start to work at higher and higher frequencies, the mechanical tolerances and the surface finish are going to become more and more important. So I think by running these tests at a lower frequency, the results should be more conclusive. Now again, I had mentioned that I have 2 of these larger horns. One of these is going to be our reference antenna. The second one will be measuring. I'm assuming that whatever I 3D print isn't going to be as good as what these 2 production horns are going to be. So this again is just kind of a baseline. As a matter of fact, if you look at the inside dimension, you can see that this horn is actually modeled after this horn. Now our circuit board horn that I've cobbled together is a little off, fairly close, but the big problem with using this as a baseline isn't so much the dimensions of the horn, it's this transition. We can go ahead and measure this, but I would expect, just because of the transition, the results for this is going to vary quite a bit. So during the first video I talked about calibrating the VNA, and I explained how we can't really do a short open load through. Normally with a coaxial line, if we apply an open, all the signal is going to be reflected back. Same thing with a short. Of course, with a waveguide, you open the end of the waveguide, the waves are just going to escape out the end of the tube. So we can apply a short, we can apply a load, but to work on this other end of the Smith chart, we can do that with a shim, for example. So this is a pretty common technique as far as doing the calibration. Another way to do it is with something that's called a sliding load. They make those for coax as well as waveguides. Now that sliding load isn't a perfect match. So let's say I've attached, instead of a 50 ohm resistor, I've attached a 100 ohm resistor. So it's a mismatch. Now what I do is I adjust the phase by changing the distance. What that's going to do is it's going to rotate around this axis. So what we can do is we can fit this to a circle, and then we can calculate the center point. Instead of a perfect 50 ohm resistor, which is going to be very difficult to make, we can use any resistor and just slide it up and down the transmission line and calculate what the perfect point is. So let me just show you what one of these looks like. Again, this part is made by Narda. This is model number 410-15. This part was probably produced in the early 60s, I would guess. We can see this has a reflection coefficient of 0.15 or an SWR of 1.353. So again, unlike the standards that are supplied with the VNA, it's not meant to provide a perfect match. And the way that we adjust this, we just loosen this thumb screw. And you can see we can just slide this in and out. And of course on the back side, we have another transition. Now I have some limited support for this now in my software. What you do is you basically start with the plunger in one position and you just extend it out some amount. And you'd like to always go in one direction. You'd like it somewhat evenly spaced, and you would like to use the full range of the slide. So typically you'll want at least 5 data points. In my software you can set it for whatever. You basically just collect as many points as you want. But what you're trying to do is get different points along this curve here. And again, what's going to happen is the software is going to fit that data and then derive the center point. Because the manufacturer does tell us what the reflection coefficient is, we can measure the VSWR with our slotted line, and we can see if the numbers that we get with that match up with what the manufacturer says. Now, of course, this testing isn't something that I do in a day. What I'm going to be showing in this video was about 3 weeks of effort. During the course of collecting all the data for these antennas, I made a pretty big mistake. So again, we use this frequency extender to test the horns, and the way we're doing that is we're attaching port 1 of the extender to our test horn, and then the receiver or the reference horn connects to port 2. So again, the horns themselves are conductive, and they're attached to our transition, which is of course also conductive, and our coax is of course grounded. So basically this entire horn is sitting at ground. So I didn't think about wearing a wrist strap because everything's at ground, essentially. Yeah, big mistake. Big mistake. So right now it's winter time and the house is quite dry, so static buildup is definitely a problem. Normally I'd wear the wrist strap, but I thought my risk of damaging anything was pretty low because everything was grounded. Again, the VNA and this extender were sitting up on the ESD mat. Now of course the tripod that the rotor is mounted to is not grounded, and it's located a fair distance away from our extender. And worse, it's sitting on top of carpet, and I have one of these plastic floor mats that I use for my chair to save the carpet. And so I'm rolling around on this chair, and I roll over to the tripod to change out our antenna, and I touch the horn, and I got this zap. And I didn't think much about it because I'm like, sure, it's all grounded, no big deal. And I go to run the next antenna, and basically the antenna's radiation pattern is total crap. As a matter of fact, it was the very first large horn that I was testing, and the radiation pattern wasn't anywhere near as good as what these small horns were. Of course, pull down the extender, start running tests where essentially I just short the 2 ports together, and I had no gain coming out of this. And what ended up happening, we damaged this amplifier here. Now I could buy the op amp that this uses. It cost about $25 a pop. Now the IC that's used in that amplifier is about this big here, and it's an 8-pin device. So I'm actually grinding down the soldering iron tip to get something small enough to lay in there to reflow the solder around that after I hit it with a heat gun. So I was able to repair the amplifier, and I went back and I baselined some of these antennas just to make sure that we didn't hurt the performance at all. Everything was fine, and we continued on our testing, but I continued the rest of the test using a wrist strap. So my advice, always wear a wrist strap. Even if you think everything's grounded, it's not worth it. By the time I ordered the parts, I got everything changed out, retested. I lost a few days just to that. So don't be stupid like I was. Looking at the software for our LiteVNA, we can go ahead and go to Advanced, and let's go to Antenna Sweep. So here we're looking at one of the horns that was supplied with the university kit, and comparing that with one of our 3D printed horns. You can see the opening mouth is quite a bit larger on our 3D printed horn. And then this again is one of our other metal horns. So I've characterized both of these. Let's just start with our small horn. So we'll use metal, small, 180 by 24. So 180 is 180 steps for the azimuth, and then the number of elevation steps is 24. If you can imagine, this is our reference antenna, and this is the antenna that we're trying to test. If the two are pointed at each other, we're going to have a very good coupling, versus as I rotate this thing up and down. So in the upper right where it says 2D elevation, where it's at 90 degrees, that's with the two facing head on. So let's just change that to 0 degrees. And now we can go ahead and save that to memory 1. So 0 degrees is facing down. Let's go ahead and change it to 180 degrees. That would be pointing up. So the red is looking down, the blue is looking up. We can save that to memory 2. And now let's change it back to 90 degrees. And that's our blue trace. And of course, looking at the blue trace, again, as the antenna rotates from the back to the front, we get the most coupling as the two are facing one another. So this is looking at the radiation pattern in 3D. Again, we can turn off the mesh, turn off the grids. So this is kind of what it looks like. You can zoom in, rotate, look underneath it. You can see the elevation is fairly limited. Again, I could increase that resolution. It's just how much time you want to spend doing the sweeps. But this gives you a good idea overall what the radiation pattern looks like. Again, I ran several tests on various printed antennas. So let's have a look at the first one. Again, that's denoted by the green number 1 here. Again, I measured the resistance of this 2 different times. I was trying to get an idea how many coats were required before the resistance stopped changing. This particular horn has 5 coats applied to it. Again, this horn has been wet sanded. I'm not sure how well this will show up on the camera, but the surface finish of this is very smooth, akin to our metal horn. So let's load up 2 coats. We'll just save that to memory number 1. And now let's load up the same antenna after 5 coats have been applied. Notice how the gain goes up even higher. So looking off to the right where it says forward level, this is the maximum gain that it measured. So a minus 48.6 dB or so. Again, I want to be clear that that's a relative measurement. I'm not changing anything about the setup. And again, the idea is just to compare the antennas using a standard setup. So certainly adding more of the coating does help. Let's go ahead and we'll save this off to memory number 1 as well. And now let's load up our second antenna. So this is looking at antenna number 2. And you can see this one has not been sanded. Notice the ridges from the printing. And the resistance of this one is roughly the same. So 0.370 versus 0.393. We'll save that off to memory 2, and let's go ahead and load it after we've applied 5 coats. And again, you can see the gain went up quite a bit. The blue trace again being after 5 coats were applied, and the yellow with 2 coats. And what's interesting is we can see this particular horn has slightly higher gain than our first horn that was wet sanded. Again, I'm looking for significant changes. This is a pretty minor difference between these 2 antennas. Let's go ahead and save this to number 2 now. And let's have a look at our third horn. Now this horn was just lightly sanded. Again, because I didn't see a big difference between those 2 antennas. And then again, this one was primed. What I did notice is using that coating with a primer helps it adhere to the plastic. And you'll notice with 6 coats now, the resistance goes down even further, a little lower than 0.1 ohms. Let's see how that affects the radiation pattern. And again, that's the blue trace. And notice between the first and second antennas, they're basically right on top of each other. So from this, I would say it's really not worth the time wet sanding these particular horns, again, based on the size. And then also applying an additional 6th coat doesn't seem to have any effect as well. Certainly not to the same degree that going from 2 coats to 5 coats had. We'll save that to memory number 2. Now let's have a look at our 4th horn. This horn is made from PLA, but this is a ESD type plastic. So you can see the resistance of this is 400 k ohms. Now this horn is straight off of the printer. I've made no attempt at sanding it. and no primer or coating has been applied to it. So the blue trace is our ESD type plastic. You can see it has some radiation pattern to it. Let's go ahead and save this off to memory 1. So another test that I had done was taking this transition by itself and sweeping it with no horn attached to it. And of course this is going to have some directivity as well. Obviously, if the two are pointed at one another, the coupling is going to be much higher than if it's pointed away. So let's have a look at that data. And that's our blue trace here. So what's actually happened, it looks like, is adding this particular horn has actually decreased the gain off of the coupler. Now again, the signal level on this is quite low, so how much did it really affect it? It's hard to say. But certainly I'd say the one thing we can take away from this is this ESD plastic, without any further preparation, is going to make a very poor radiator. So now let's move on to our larger horns. So this is horn number 5. Just like before, I collected data for this antenna with 2 coats as well as 5 coats. So let's go ahead and load the data set based on 2 coats. And this is what it looks like. We can go ahead and save that to memory number 1. And now let's load up the same horn with 5 coats applied. And this is what it looks like. So again, you can see there's a dramatic difference between applying 2 coats and 5 coats. The gain is much better. Now let's go ahead and we'll save this to memory number 2. Now notice there's another one here called ESD. Again, early on I said the very first large horn that I tested is where I blew up that amplifier. That happens to be this horn here. So that's the blue trace here, and you can see what's happened is the gain went way down. So it was definitely some directivity, which kind of leads you to believe that things are somewhat working, but with it being such a low gain, I knew something went wrong. So the yellow trace was after I had repaired the amplifier. So test horn number 6 is also made out of that ESD plastic. This one happens to measure 680 k ohms across it. Let's see how this data looks. And again, that's the blue trace down here. And again, just like the smaller horn that was printed with the same plastic, you can see the radiation pattern with this larger horn is once again very poor. Let's go ahead and we'll save that to memory number 1. And now let's have a look at horn number 7. This is made out of a conductive PLA. This particular horn measures 182 ohms across it. And again, this horn is basically the way that you're seeing it coming off of the printer. No attempt was made to sand it or anything. So again, we'll select load and we'll load up horn number 7. And notice how the forward gain for this antenna is basically identical to what we saw with our horn printed out of the ESD type plastic. So my hopes with this particular horn, again, having this conductive plastic, was that I could possibly plate copper onto this directly. Unfortunately, all my attempts to plate this type of plastic directly at home have failed. So this is the last 3D printed horn that I tested. This one has been wet sanded, and it also has 5 coats on it. Let's go ahead and load that up. So notice how antenna number 8 has higher gain than number 5 here. So again, this one has not been wet sanded. The same number of coats between these two. And also notice the DC resistance of this horn is slightly higher than for our other horn. But again, I wouldn't say that this is a real significant difference between these two horns. So now again, the real question is, how do these compare against our metal horn? So let's have a look at that. And here we have it. So again, our blue trace being the metal horn, and the red being horn number 8, and you can see these two basically lay right on top of each other. So my conclusion with this is it's certainly possible to 3D print a plastic horn and then coat it and have it perform just as well as its metal counterpart. If you've looked at metal horns like this and priced them out, this horn would be quite a bit cheaper. Again, that coating costs about $80, I think, for a can of that. And I probably have about half of that coating left after applying that to all these different horns. It may actually be cheaper to buy a printer and the coating, print your parts, than to buy a single horn. So again, here's our different horns that we tested. So for example, this is looking at our smaller metal horn. So we can see the forward level in dB is a minus 47.7 or so. And this is our azimuth half power beam width. So for this, what we're looking at is This is our peak power when the two are pointed at each other, and as I rotate it in this axis, not this, as the power is cut in half, I'm measuring how many degrees of rotation that is, so 36 degrees in that case. The next column is the plus minus 30 degree reversal level, so think of the antenna basically pointed backwards, and that may or may not give you the least amount of power. So what you do is you're going to rotate this thing plus or minus 30 degrees, and then we're taking the average of that power. The next column is the DC resistance, and then we start looking at the VSWR. So looking at the forward level for the large metal horn, it's a minus 42.2, call it. So if we look at horn number 5, the large PLA unsanded 5 coats and the large PLA wet sanded 5 coats, you can see these are like right in the same ballpark as what our metal horn is. Also notice that the half power beam width, it's 22 for our metal horn versus 20 and 18 degrees for the other two printed horns. Now of course the DC resistance for these two metal horns is a lot lower. So looking at our small metal horn, it's 0.0083 ohms. Looking at the large horn, it's 0.0082. So we're basically down to what that 34401A meter I've got can measure. So in order to make these surface measurements, I'm using a set of 4-wire Kelvin leads. Now of course you can't just clip these directly onto this because surface area, first of all, is pretty small, and the leads are actually attached to the two different clips here. So these have to be connected together. The coating's only applied to the one surface, so we have to work around that, and the way I'm doing that is I made these clips. I put these over the two locations that I wanted to measure, and then I took a paper clip and I clamped it down like so, and I did the same thing for the front with the other one here, and then I'm attaching our Kelvin leads to our strap like so. It's actually quite repeatable, but my point to this is that even though the resistance for the metal horns is quite a bit lower, comparing the radiation patterns between the metal and the 3D printed plastic horns, there's basically no difference. So with the coated horns having a slightly higher DC resistance, it doesn't appear to affect the radiation pattern. So while I mentioned that I used the frequency extender to measure these horns, I didn't talk about the frequency that I ran them at. You may remember when I first showed that frequency extender and I had it hooked up to my frequency counter, I was running the LiteVNA at 2.3 gigahertz, and then the frequency extender converts that to 10.16 gigahertz. So when I ran these horns, I ran these at that same frequency. So all this data is for 10.16 gigahertz. So if we look at our next column, you can see it's VSWR, and notice it's pretty high. It's like 3.9, 2.75. So to take these VSWR measurements, I'm using this Narda coupler, and I'm running this again at the 10.16 gigahertz. And again, this has only been characterized up to 8.3 gigahertz. You can see the calibration factors, though it's fairly flat. And then I'm applying an SOL to this connector here. After doing that, I'm taking a coupler and I'm attaching our transition like so, and then I'm measuring our horn out here. The interesting thing here is, again, if we look at the ESD type plastic, notice that the SWR is 3.5 or so to 1 versus about 5 to 1 or 4.6 to 1. So it's actually better with that ESD plastic. And again, looking at our larger horns, here's our ESD plastic at 3.42 to 1 versus 4.8, 4.38, and 4.2. So if we're just looking at VSWR, it looks like the ESD plastic does the best job of all of them, but again, the radiation pattern tells a completely different story. So you may look at this data and think either the calibration standards were poor, or adding this transition along with its coupler and the additional coupler to tie these two together is just a poor idea, and that's adding a lot of error. But there's one other test here that I performed this way. Remember the sliding load? And again, remember the VSWR of this is 1.353 to 1. So I took this and I attached this directly in place of our other transition. So I had the same coupling here. And if we look here where it says sliding load standard, Notice it's 1.375 to 1 versus 1.353 to 1. So the error in all my other VSWR measurements probably isn't so much due to the standards that I used or the additional coupler. Something else is going on. So remember, again, I said I bought these from one of the university waveguide training kits, and one of the components I have is this slotted line. And again, we can use this not only to measure the frequency, we can also use this to measure the VSWR. Again, this has a diode detector inside of that, so I'm using a multimeter attached to this point here. So if I can get this in the light, maybe right there you can just see the probe tip. You can see how I can slide this up and down. So I went ahead and I used this to measure the VSWR, again taking each horn and attaching it directly to the flange like so. Before I made those measurements, I again took our sliding load with its SWR of 1.35 to 1, and I removed our transition here, and I basically attached this directly to the flange of our slotted line. So this first column is looking at the maximum voltage, and then the next column is our minimum voltage, and the next column is our VSWR. Again, we're taking the maximum divided by the minimum, and we're taking the square root of that. So we come up with 1.31 to 1 versus 1.35 to 1. So again, very close to what the standard is marked. So then if we kind of look at the rest of these antennas, our smaller metal antenna was 1.2 to 1, and then our large metal antenna is 1.12 to 1. And now let's have a look at our 3D printed parts. Again, 1.2, 1.2. Now let's have a look at our ESD horn. It's 1.33 to 1. And the same thing if we look at our larger horns. The horn made out of our ESD plastic is 1.38 to 1. And then our conductive unsanded plastic is 1.13 to 1. Comparing that with our two standard PLA horns with 5 coats applied. This first one again being unsanded versus sanded at 1.10 versus 1.27 to 1. Again, what's the difference in making the VSWR measurement using a slotted line with the horn directly mounted to it versus trying to measure it with this directional coupler? Well, again, we said we took our sliding load, we had it attached directly to the flange, and we got pretty much the correct answer. And of course, the other thing I said I did is I took this sliding load with this coupler and I attached it directly to our directional coupler here, and again we came pretty close to the correct number. So what's the difference? Of course, this cheap transition versus the one that I have on the standard. So for the next test, I took this transition and I mounted that directly to this horn, and then I attached it to our directional coupler just like before. Let's have a look at that data. And now you can see I'm measuring 1.04 to 1 on the smaller horn. Originally using this coupler, again that's the only thing that's changed, we measured 4.86 to 1. That much error is caused from this coupler. So again, I repeated the test using the larger horn, and you can see I measured 1.16 to 1 versus originally 3.9 to 1. So then what I did is I took our last 3D printed plastic horn. Again, this is slightly the best performer out of all the 3D printed horns, and I measured this using the better transition, and I got 1.08 to 1 compared to 4.38 with the other transition. If you're curious how my original printed circuit board antenna works, let's just go ahead and load that up. Again, PCB large. And that's our blue trace here. Well, again, this is dimensionally fairly close to our metal antenna. Again, the big difference is that we're using a different transition. So it looks like our forward gain is a little lower, which shouldn't be too surprising. So far, for most of our experiments, I've made my own waveguides out of hobby brass. Again, this is looking at our slotted waveguide. A lot of people had commented about this as far as how to improve it. I want to be clear that during the start of that video, I hooked that frequency extender up to a frequency counter. They do have newer technology. It's not like you actually need to make something like this to measure frequency. You could, but if you could go out and buy a frequency counter for next to nothing and get a very accurate measurement, there's probably not much of a reason to build something like this outside of just for your own personal curiosity, or, you know, making a video like this where I'm demonstrating it to you. So personally, I wouldn't put a lot of effort into making something like this. As a matter of fact, you can still find slotted lines on eBay. I saw one from HP that looked like it was all complete, and they wanted something under $100 for that. That would be very well made, a lot more precision than what you're going to make at home. And I think that you'd be a lot better off going that route than trying to make something. I actually saw a student's PhD, I believe, paper. I believe that that paper was fairly recent. I mean, recent within probably the 1980s, 1990s. Anyway, they had taken a slotted line. They hooked up a stepper motor to it and a screwdriver so they could actually automate moving that. And essentially what they had done is they made this mechanical VNA. And I thought, you know, you could get this pocket VNA for 120 bucks. It's going to outperform anything you can do with all these crazy stepper motors. Why would you ever do that mechanically? But that's what their paper was. So interesting stuff when you look out on the internet as far as what you can find. Anyway, I wanted to purchase some waveguides, and I looked for some WR90 material to try to basically stay with what we have here. And while I couldn't find anything, I did come up with this WR102 standard. This is 25.9 on the broad width and 12.95 on the height. That's in millimeters. Interesting thing with this is we can see it's a lot thicker. This, I believe, was 0.32 thousandths. Just look at the meat on this. The other thing is this is an extruded piece, so we actually get square edges, and dimensionally this is going to be correct. Also notice it's silver plated. This particular piece has also got a heavy zinc coat primer, and then I believe that this is powder coated. With it being a slightly larger waveguide, of course the frequency will operate a little bit lower. So the WR102 standard is rated all the way down to 5.78 gigahertz and up to 11.571 gigahertz where it changes modes. So I've homemade a couple of transitions here. This particular connector is off of some old test equipment, and this is actually an airline connector, very high quality. The other is a standard stainless steel SMA, and then you can see I've added some additional set screws in here, and that was to allow me to tune these. Somebody had posted in the LiteVNA groups IO where they were trying to run some tests above the 9.3 gigahertz that they limit this thing at, and so Dislord had posted a version of firmware up there for them. I tried to load it into one of these because I was curious about that as well. I know the performance of this is pretty poor once you get into that 9.3 gig, but that doesn't mean that it's not usable beyond that. So I tried to load the firmware into this. I noticed right off the bat I could no longer communicate to it using my software, so something in the protocol had changed. So I reached out to Dislord, and he provided me with the firmware that I have here today, and this firmware tops off at 18 gigahertz. Now, of course, he was very clear. This firmware is for experimentation only, and of course I don't think anybody's going to think that as we move beyond 9.3 gigahertz that this thing's going to get any better. Of course, it's going to get worse. So I went ahead and installed that, and it's been working fine. One of the very first things that I did after installing it, you remember this filter here? This was tuned for somewhere around 10 gigahertz. I attached this filter directly to the VNA, and then I measured this thing. And then I compared that data when I had measured the filter with our frequency extender attached to the LiteVNA. I was actually quite surprised that we could see anything at all. So for these tests, I'm going to be running this waveguide at a little lower frequency, and will stay inside the working range of the LiteVNA. So I won't be using our frequency extender for this test. And part of the reason that I want to do that is because this is an experiment that you could actually perform at home without too much difficulty. So we'll go ahead and we'll torque all of our connectors. Now we'll go ahead and link to the VNA. Now let's go ahead and select the setup diagnostics. You'll notice this new selector called external coupler. If you enable that, the software is going to use port 2 data for the port 1 reflection measurement. So if you want to experiment using an external coupler, that's how you do it. So let's go ahead and we'll select main. And what I'm going to do is change our stop frequency to, we'll say 10 gigahertz. And let's go ahead and enable our sweep. And now let's select transmission rectangular. Now let's just grab our cursor and we'll move it over to this edge over here. And we can see it measures roughly 5.788 gigahertz. And remember, we said for the WR102, the lower cutoff is 5.78 gigahertz. We're basically spot on with what this is rated for. So it looks like the waveguide is doing its job, and you can see he actually allows you to run this all the way up to 18 gigahertz. But again, the data up here would be totally bogus. Next, what I'd like to do is go ahead and calibrate the instrument. So we're going to select 2-port cal, hold, and I'm just going to grab this file here called calibration. And you can see we calibrated this for a lower frequency of 6.6 to 6.7 gigahertz. So well within the working range of this particular waveguide. The other thing about working with this lower frequency is the performance off of the LiteVNA is going to be good enough to where we can actually make some measurements here. So let's just go ahead and we're going to store this data to memory 1. And the next thing I'm going to do is remove this transition. Doesn't matter which one. This one happens to be attached to port 2, so this is the receive side. Alright, so this is looking down inside of our waveguide. Here's our transition on the right. You can see my stub down inside of there. And this is looking at our main waveguide. Notice that the flanges are a little different. One of the reasons for that, remember, is I talked about gas fill in these waveguides. And so what you would normally do is apply an O-ring. Fits in this groove here, and that allows it to hold pressure. Another reason for this feature is the coupling. The other nice thing about these waveguides is, notice again, these are all silver plated. Now looking again at the VNA, you can see as I've separated these apart, we're measuring somewhere around, I don't know, 38, 40. What we can do here is change our IF filter. We'll select 1 kilohertz. Try to help with the noise a little bit. And I'm going to save this off to memory number 2. So this gives us our 2 ranges again as I kind of start to put these two together. See how it comes right back to where it was? So I can actually just hold these finger tight and get a fairly decent measurement with this. Again, I talked about using paper clips to hold these flanges together, and it works just fine for the testing that I'm doing here. You're not going to make a metrology grade measurement that way, I'm sure. So in my hand here I have a couple of different pieces of material. I believe this is a piece of Lexan, this is a piece of rubber, and this is a piece of Teflon. So what I'm going to do is we'll start with our piece of rubber. I'm just going to insert that into our transition like so. Nothing fancy. And now I'm just going to hold these 2 flanges together. And you'll notice how that changes what the waveform looks like. What I'm going to do is just save this off to memory number 1 now. So again, here we have a piece of Teflon. And again, we'll just replace that into the end of it like so. And look at that. It's completely different than the rubber. Let's go ahead and save that to memory number 2. Now, I'm sure you're thinking, oh, the setup is probably different. First of all, let's just decouple the 2. And now let me put them back together. Again, you can see it basically goes right back to where it was. Again, back apart. And here we are together again. Let's go ahead and we'll take out our Teflon. And let's reinsert our piece of rubber. And let's see how repeatable it is. Again, just down inside like so. And look at that, it goes right back to where it was. So this is a piece of Lexan. And again, we'll just insert it in the end of it like so. And let's see if this is any different. Again, that's the red trace, and sure enough, you can see we get a completely different signature again. Of course, this isn't anything groundbreaking. I had found a paper that HP had published maybe in the 50s or something where they were looking at properties of different materials, and one of them happened to be BEO. But they went over the different methods on how you could measure the different materials. And of course, one of them is just using a rectangular piece of waveguide and putting the material directly in the center. Different fixtures have different pros and cons to them. But I thought it's kind of interesting that you could use something as simple as a piece of waveguide like this to measure different materials. So that'll conclude part 3 of my introduction to waveguides. If you'd like to see a part 4 and you have some suggestions as far as what to show, feel free to leave them in the comments. There's just a couple of things I'd like to go over before I close this video out. This is a copy of the manual that would have been provided with our microwave training kit. You can see this is produced by Electronic Research Labs. While I did receive a lot of the components in this kit, I didn't receive the controller. This runs through several experiments, but at the start of every experiment, they go over the safety, and of course they talk about the klystron tube getting extremely hot and how you can get burned. But I want to point out caution number 3, RF power levels in this kit are not harmful, but a human eye may be damaged by low levels of radiation. Do not look into any waveguide at any time when the units are on. I didn't do a lot of research to see at what level the eye can become damaged, but I know these oscillators like this one here are fairly low power. So the point being, if you're going to play with microwaves, you want to exercise some caution. The only thing I'd mentioned earlier on was the flange, and I showed you how this gasket fits in this area here. This is called a choked flange. Again, you're normally going to mount this choked flange against a flat one. What I want to show you is that this is not flat across the face of this. You can see there's a gap there. Also notice this other deep recess. And of course, there's a reason that this is called a choke flange, and you can find that information readily available on the internet. I would imagine when I was about 12 years old or so, a friend of the family's had given me this book. This was published by RCA. This is called the Field Engineer's Technical Manual. You can see the date that this one was published was in 9/14 of 1960. And you can see this book is just packed with information. It's got everything from transistors to vacuum tubes, matching circuits. Here we have a chart of the teletype character set. You can notice it has a section on waveguides, and I'd like to go over some of that. And here we have a section called Practical Facts About Waveguides. So let me just read this. Usually where two waveguide sections are joined in such a fashion as to be quickly removable, an RF choke is used. So we can see it's a 1/4 wavelength deep slot closed at the bottom. Acts as an RF choke for RF signal which might try to get out in the direction perpendicular to the axes of the waveguide. This is only for rectangular waveguides. But again, here we have the waveguide in the center, and we can see 1/4 wave deep slot milled in a circular piece of metal brazed to the waveguide. But notice this very last comment. An acoustic analogy, RCA tone guard, is shown above. The slots around the inside of the cabinet act as chokes to prevent undesired high frequency sound that is radiated by the vibrating parts of the phonograph pickup from getting out through the normal gap between the lid and the cabinet. I've never seen the choke flange explained that way, so I just thought that was kind of interesting. If I do make a part 4, I'd like to go over this device here. This is known as a Magic T. This has some very interesting properties. One thing we could possibly use this for is part of a detector. So I think that's going to be it for this video. Hopefully you've enjoyed it. Looks like the channel has grown quite a bit. It's up to 22,000 subscribers now. Crazy. I was surprised when it got to 2,000. Again, I don't have a Patreon or a PayPal account, so we don't accept donations for this channel. This is all just for free of charge. So I appreciate those of you who are here and enjoy learning along with us. Hopefully we'll see you in the next video. Later.